There is a moment in the story of this continent that nobody talks about. Not in schools, not in documentaries, not in the textbooks that get passed around to children who are just beginning to learn that humans have been here for a very long time. It is a moment that happened before cities, before agriculture, before anyone thought to carve their name into stone or press their fingers into clay. It happened in a world that looked almost nothing like the one we live in today, and yet it was populated by people who were just as curious, just as intelligent, just as driven by the need to survive and belong, and make sense of the darkness around them as you and I are right now. Something happened to those people, something enormous, something that we are still, after decades of excavation and argument and satellite imaging and chemical analysis, struggling to fully understand. And the harder scientists look, the stranger the picture becomes. If you are lying here in the dark, somewhere between wakefulness and sleep, letting someone else's voice carry you through the quiet hours, then you are in exactly the right place for a story like this one. These are the kinds of stories that deserve the dark. They deserve the quiet. They deserve the long, slow attention of a mind that is not rushing anywhere. If you're watching this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where are you right now and what time is it. So let us begin at the beginning. Or rather, let us begin near the end. Because sometimes the most honest way into a mystery is not through its origins, but through the silence that came after. Imagine standing on the North American continent approximately 12,800 years ago. The world you are standing in is colder than ours, but not uniformly so. The great ice sheets that had once covered enormous swaths of what would become Canada are retreating, slowly, the way glaciers always retreat, grinding down the stone beneath them, leaving behind lakes and rivers and valleys that will not be named for thousands of years. The sky is wider somehow. There are fewer trees in the north, more open grassland, more sky pressing down on the horizon. The animals are unlike anything alive today. Mammoths move in slow herds across the open plains. Mastodons browse along the edges of forest and grass. Giant ground sloths, animals the size of modern elephants, pull branches down with hooked claws. Horses, the original North American horse that would eventually go extinct on this continent and only return much later with European settlers, graze in mixed herds alongside camels, yes, camels, that evolved here in North America before spreading to other continents. Short-faced bears, larger than any grizzly alive today, patrol the landscape. Dire wolves hunt in packs. Saber-toothed cats, still proval, still exist, still make the grasslands dangerous in a way we can only imagine now. And moving through all of this, living in all of this, are human beings. They are not primitive in the way that word is sometimes used to dismiss people who came before written history. They are anatomically identical to us. Their brains are the same size. Their capacity for language and love and grief and curiosity is the same as ours. They are simply living in an earlier chapter of the same story. They have been in North America for at least 15,000 years by this point, possibly longer. The debate continues and probably always will, and they have spread across the continent with remarkable efficiency. From the frozen north to the southern tip of South America, human beings have made themselves at home. They know the land, they know the animals, they know the seasons and the rivers, and the places where the grass grows tallest, and the places where the water hides beneath the stone. The people who left the most visible mark on this particular moment in time are the ones we call the Clovis people. That name does not come from anything they called themselves. We will never know what they called themselves. It comes from a small city in New Mexico called Clovis, where, in Tisits Deviatset Dvatset Deviat, a cowboy named Ridgely Whiteman found something in an arroyo, a dry gully carved by floodwater, that would change everything we thought we knew about who got to the Americas first and when. He found spear points. Long, beautiful, carefully made spear points with a distinctive groove, a flute, carved into the base that allowed them to be hafted onto wooden shafts. He found them mixed in with the bones of extinct animals, mammoths, the kind of animals that had been gone from this continent for thousands of years. And so the question that followed was obvious, unavoidable, and extremely uncomfortable for everyone who had built careers on the assumption that humans had arrived in the Americas relatively recently. If these spear points were mixed with mammoth bones, then the people who made these spear points had lived here when mammoths still walked the earth. That was the beginning of a conversation that has never really stopped. For decades after Clovis, the dominant story went something like this. The first Americans crossed a land bridge called Beringia, a wide stretch of land that connected what is now Siberia to what is now Alaska, during periods when sea levels were lower, because so much water was locked up in glacial ice. They crossed this bridge, these first pioneers, and then they moved south through a corridor between two massive ice sheets, the Laurentide and the Cordilleran, a corridor that opened up as the glaciers began to retreat. They spread south, and as they did, they became the Clovis people, the first Americans, the founders of everything that followed. This was called the Clovis First hypothesis, and for a long time it was treated almost like settled fact. It is not settled fact. It was never quite settled fact. And in the last 30 years, the evidence has accumulated to the point where almost nobody defends Clovis First in its original form anymore. Pre-Clovis sites have been found, carefully excavated, carefully dated, carefully argued over. A site in Chile called Monte Verde holds evidence of human habitation that predates Clovis by at least 1,000 years, possibly more. A site in Texas called the Deborah L. Friedkin site has yielded stone tools that are older than Clovis by thousands of years. Human footprints found in New Mexico at White Sands National Park, preserved in ancient lake sediment, have been dated to somewhere between 21,000 and 23,000 years ago, which, if those dates hold up under continued scrutiny, would push the arrival of humans in the Americas back to a time when the Beringia land bridge route was essentially impossible because the glaciers would have blocked the path south. So the story is messier than we thought. The arrival was earlier, or multiple, or both. There may have been coastal routes hugging the Pacific shoreline in boats or on foot along ice-free stretches of coast. There may have been more than one wave of migration, more than one group of people finding their way to this continent from different directions at different times. The question of who the first Americans were is still genuinely open, which is both deeply frustrating and endlessly fascinating. But here is what matters for our story tonight. Whatever their origins, by 12,800 years ago, human beings were living across the entire Western Hemisphere. They had been here long enough to develop distinct cultures, distinct technologies, distinct ways of reading the landscape and finding food and building community. And then something happened. Something that left a mark in the geological record so distinctive, so unusual, so different from anything that came before or after in the same time period that scientists are still arguing about what caused it. The event is called the Younger Dryas. That name is even less romantic than Clovis. It comes from a small Arctic flower called Dryas octopetala, a plant that thrives in cold, open conditions and whose pollen began appearing in enormous quantities in European sediment layers, precisely at the moment when the climate took a sudden, dramatic, terrifying turn toward cold. The Younger Dryas was a period of rapid cooling that began approximately 12,900 years ago and lasted for about 1,200 years, ending roughly 11,700 years ago. During this time, temperatures in some parts of the northern hemisphere dropped by as much as 10 to 15 degrees Celsius within decades. Not centuries, not millennia. Decades. To put that in perspective, the difference in average global temperature between the depths of the last ice age and today is only about 5 degrees Celsius. The Younger Dryas, at its onset, produced temperature swings of double that magnitude in some regions, and it did so with a speed that would have been genuinely catastrophic for any ecosystem, any animal population, any human community trying to plan its survival around the rhythms of a climate that suddenly, violently changed the rules. And at the same moment that this climate catastrophe began, something else happened, something that the geological record captures in a thin, dark layer of sediment found at sites across 4 continents, a layer that contains things that should not be there. nanodiamonds, magnetic spherulis, iridium, platinum, shocked quartz, high-temperature melt glass, carbon spherules that form only when organic material is burned at temperatures far beyond what any natural wildfire could produce. Lonsdaleite, a hexagonal form of diamond that, on Earth, forms almost exclusively from the intense heat and pressure generated by a large extraterrestrial impact. This layer, which geologists call the Younger Dryas boundary layer, or YDB, is found at the same stratigraphic level, which is to say at the same moment in time, at sites from California to South Carolina, from Belgium to Syria, from Chile to South Africa. It sits right at the beginning of the Younger Dryas cooling event. It sits right at the level where the Clovis culture, the most widespread and recognizable archaeological culture in North America at that time, essentially disappears from the record. And it sits right at the level where the megafauna begin to vanish. The mammoths, the mastodons, the ground sloths, the horses, the camels, the short-faced bears, the dire wolves, the saber-toothed cats, 37 genera of large animals representing species that had survived multiple previous ice ages, that had lived through previous periods of dramatic climate change, that had coexisted with human hunters for thousands of years, suddenly, geologically speaking, almost simultaneously, went extinct. This is called the Quaternary extinction event, and it is one of the great puzzles of paleontology. The debate over what caused it has been going on for more than a century, and there are two camps that have dominated the argument almost from the beginning. The first camp says it was the humans. The second camp says it was the climate. And for decades, neither side could decisively win, because neither explanation, on its own, quite fits all the evidence. The human explanation, called overkill, was most powerfully articulated by a biologist named Paul Martin in the Thesetes deviat set Shadesarts. His argument was straightforward. Large animals that had evolved in places without human predators were naive. They had no fear of the strange upright creatures that appeared on the landscape carrying sharp sticks. And humans are extraordinarily effective hunters when their prey does not run from them. We can see this pattern repeated elsewhere in the historical record. When humans arrived in Australia, the giant marsupials began disappearing. When humans reached Madagascar, the elephant birds went extinct. When Polynesian voyagers reached New Zealand, the moa were gone within a few centuries. Every time humans arrived somewhere new, carrying their weapons and their hunting knowledge, the largest, slowest reproducing animals tended to disappear first. The argument against pure overkill is that the timing doesn't always line up. In North America, humans and megafauna coexisted for thousands of years before the extinctions happened. If human hunters were so devastatingly effective, why did it take so long? And why did so many species disappear so suddenly at the end, rather than gradually, the way you would expect if hunting pressure were the primary driver? The climate explanation says that the rapid cooling of the Younger Dryas disrupted the ecosystems that large animals depended on. Grasslands turned to forest or tundra. Seasonal patterns of plant growth shifted. Migration routes that animals had followed for thousands of generations were blocked or altered. Animals that had survived previous ice ages did so because those transitions, while dramatic on a geological timescale, were still slow enough to allow adaptation. The Younger Dryas came too fast. The argument against pure climate is that these animals had survived previous rapid climate shifts. There had been other cold snaps, other periods of dramatic ecosystem disruption during the Pleistocene, and the megafauna had made it through. Why was this one different? And that is where the third explanation enters the room. The one that is still controversial, still fiercely debated, still generating new papers and new arguments and new evidence with every passing year. The explanation that suggests something came from the sky. The idea that a large extraterrestrial object, perhaps a comet that had fragmented into multiple pieces, perhaps an unusually large cluster of cosmic debris, struck or airburst above the North American ice sheet approximately 12,900 years ago, triggering the Younger Dryas cooling event, igniting continent-wide wildfires, disrupting the atmospheric chemistry that drives weather patterns, and effectively ending the world that the Clovis people and the megafauna had known. This is called the Younger Dryas impact hypothesis, and the scientific team that first formally proposed it in 2007 did not expect quite the reception they received. The reception was, to put it diplomatically, mixed. To understand why, you have to understand something about how science works. Science is a human enterprise, and human beings are creatures of habit and investment. When you have spent decades building a career on a particular explanation for a historical event, when your textbooks and your lectures and your reputation are all built on a certain understanding of the past, the arrival of a new hypothesis that potentially overturns everything is not welcome news. This is not a criticism of scientists. It is a description of how knowledge changes, slowly, painfully, against resistance, the way it has always changed. The Younger Dryas impact hypothesis arrived at a moment when the impact science community was already riding high on a significant victory. The discovery in the 1018 Deviatset 19 to the mass extinction at the end of the Cretaceous period, the one that killed the non-avian dinosaurs, was caused by a large asteroid impact, had been one of the most dramatic revisions in the history of geology and paleontology. For decades, that idea had been resisted. Then the iridium layer was found, then the crater was identified in Mexico's Yucatan Peninsula, and the story became settled science. The impact community was not wrong to feel that extraterrestrial events could cause mass extinctions. They had the dinosaurs to prove it. But the Younger Dryas impact was a different kind of claim. For one thing, there was no crater. Or rather, there was no obvious crater, no single smoking gun like the Chicxulub structure in the Gulf of Mexico. And for another thing, the extinctions at the end of the Pleistocene were not as total, not as sudden, not as devastating as the Cretaceous event. Large animals went extinct, yes, but many species survived. The event was catastrophic, but not extinction level in the dinosaur sense. So the question the critics immediately asked was this: if a large extraterrestrial object struck the Earth, where is the crater? And the answer that the proponents of the hypothesis offered was not a simple one. The target, they argued, was not bedrock. The target was ice. The Laurentide ice sheet, which covered most of Canada and extended well into the northern United States, was at the time of the proposed impact between 1 and 3 kilometers thick in many places. A large object, or a swarm of objects, striking the top of that ice sheet would not produce a conventional crater. The energy of the impact would be absorbed and transmitted through ice, triggering catastrophic melting and flooding, possibly disrupting the circulation of the North Atlantic Ocean, potentially launching enormous quantities of water vapor and debris into the atmosphere, and leaving behind exactly the kind of geological signature that the YDB layer displays. Widespread, distributed, showing evidence of intense heat and pressure, but not localized to a single impact site. This explanation is coherent. It is physically plausible. It explains the absence of a crater, but it is also, almost by definition, very difficult to confirm because the ice sheet itself is gone. It melted. Whatever record it held of whatever struck it is dispersed now, spread across the bottom of the North Atlantic Ocean, buried under centuries of sediment, or washed away entirely, which means we are left with the evidence in the sediment, the YDB layer. And the argument about that layer has been going on since 2007 with a ferocity that is unusual even by the standards of scientific debate. The original 2007 paper by Richard Firestone and a large team of colleagues reported finding a suite of markers in the YDB layer at multiple sites across North America. The markers included high concentrations of magnetic spherules, which are tiny spherical particles that form when material is melted and then rapidly solidified, typically in an impact or explosion event. They included nanodiamonds, microscopic diamond crystals that form under conditions of extreme pressure. They included elevated levels of iridium and platinum, elements that are rare in the Earth's crust but relatively common in certain types of extraterrestrial material. And they included a layer of charcoal and soot consistent with widespread, continent-scale wildfires. The response from the scientific community was immediate and sharp. Critics went back to some of the same sites and reported that they could not replicate the findings. They said the nanodiamonds were not actually nanodiamonds, or were not present in the concentrations claimed. They said the magnetic spherules were common in sediment generally and could be produced by ordinary processes. They said the iridium anomaly was not statistically significant. They said the charsol layer was consistent with ordinary regional wildfires, not a continent-spanning conflagration. The proponents went back and did more work. They found more sites. They refined their methods. They published more papers. The critics published more rebuttals. The proponents answered the rebuttals. And this back and forth has continued, escalating in some ways, for nearly 2 decades. What makes this debate so difficult to resolve is that the evidence itself is genuinely ambiguous in places. Nanodiamonds, for example, turn out to be more complicated than anyone initially realized. There are different types of nanodiamonds, formed by different processes, and distinguishing between them requires extremely precise analytical techniques that different laboratories perform differently. 2 teams, using what they describe as the same method, can look at the same sample and reach different conclusions. This is not fraud or conspiracy. This is the genuine messiness of cutting-edge science, applied to materials that are found in microscopic quantities in samples taken from sites that were laid down 12,000 years ago. But here is what has happened in the years since Dvartisitsa, and this is important. The evidence has grown, not shrunk, grown. New sites have been added to the YDB database. The layer has now been confirmed at more than 50 sites across 4 continents, including locations in North America, Europe, the Middle East, and South America. Each new site that shows the same suite of markers at the same stratigraphic level adds a piece to the puzzle. You can argue about the interpretation of the evidence at any single site. You cannot so easily dismiss the pattern when it appears at 50 sites spread across 40% of the planet. A significant Dvartisitsa paper by a team that included Christopher Moore from the University of South Carolina reported finding the YDB layer at a site in South Carolina with an extraordinary concentration of platinum. The platinum anomaly at this site was one of the highest ever recorded in the geological record outside of major impact craters. It was not a small signal lost in the noise. It was a large, clear, unmistakable spike right at the YDB level. Platinum is interesting for several reasons. Like iridium, it is an element that is relatively rare in the Earth's crust, but more common in certain types of meteoritic material, particularly in a type called enstatite chondrites. The presence of elevated platinum in the YDB layer at multiple sites is exactly what you would predict if a platinum-rich extraterrestrial object had entered the atmosphere and distributed its material across a wide area. And critically, unlike some of the other markers that have been disputed, the platinum anomaly is relatively straightforward to measure and replicate. Different laboratories using different methods have confirmed elevated platinum in the YDB at multiple sites. There is also the matter of the Greenland ice cores. The ice that has accumulated in Greenland over thousands of years preserves a detailed record of atmospheric chemistry, including the chemical signature of cosmic impacts. And in the Greenland ice cores, at the level corresponding to approximately 12,900 years ago, there is a spike in platinum concentrations. This is not soil. This is not sediment that could have been contaminated or misinterpreted. This is ice, laid down layer by layer, year by year, preserving a record of what fell from the sky. And what fell from the sky at that moment, according to the platinum signature, included something extraterrestrial. Now, let us talk about fire. One of the most striking aspects of the YDB evidence is the indication of widespread burning. At many of the sites where the YDB layer has been identified, it sits beneath or within a layer of charcoal and carbon-rich sediment that is thicker and more widespread than you would expect from ordinary regional wildfires. This burning event appears in the sediment record at sites across North America, from the Pacific coast to the Atlantic, from the Gulf of Mexico to the Canadian border. It also appears in European and Middle Eastern sites at the same stratigraphic level. The argument from the impact camp is that a large extraterrestrial object, fragmenting as it entered the atmosphere, would have produced multiple airbursts, explosions occurring above the ground rather than at the surface, each releasing enormous amounts of thermal energy. The Tunguska event of 1019 scale that up to an object hundreds of meters or kilometers in diameter, and the thermal energy released would be sufficient to ignite wildfires across enormous areas simultaneously. The argument from the critics is that widespread burning events occur for many reasons. Climate change can dry out vegetation and make it more susceptible to fire. A single large lightning storm, or a series of natural fires, could produce a charcoal layer that looks similar to what the impact proponents are describing. And the dating of charcoal layers is notoriously difficult, with enough uncertainty in radiocarbon dates to make it hard to say definitively that all these burning events happened at exactly the same moment. But the impact proponents have a response to this too. The burning signature in the YDB layer contains not just ordinary charcoal, but specific types of carbon spherules, microscopic balls of carbon that form only when organic material is burned at temperatures exceeding 1000 degrees Celsius. Normal wildfires do not reach those temperatures consistently over large areas. The temperatures required to produce the carbon spherules found in the YDB layer are more consistent with what you would expect from an airburst event, where the thermal pulse from an exploding object heats everything beneath it to extraordinary temperatures for a brief period. And then there is the melt glass. At a site in South Carolina and at other YDB sites, researchers have found what is called siliceous scoria, a type of glassy material that forms when rock is melted at very high temperatures and then rapidly cooled. This material is similar to the trinitite that was found at the Trinity nuclear test site in New Mexico, the glass that formed when the heat of the first atomic bomb melted the desert sand. It is also similar to the impact glass found at known meteorite impact sites around the world. It does not form in ordinary wildfires. It does not form in volcanic events in the regions where the YDB sites are located because those regions are not volcanically active. The most straightforward explanation for siliceous scoria in a sediment layer is that something produced enough heat to melt rock, and that the most likely candidate for something producing that much heat is an extraterrestrial impact or airburst. So we have, in this sediment layer, a suite of evidence that includes platinum and iridium anomalies consistent with extraterrestrial material, nanodiamonds and Lonsdale consistent with impact shock pressure, magnetic spherules consistent with material that was melted and rapidly solidified, carbon spherules consistent with burning at temperatures far beyond ordinary wildfires, siliceous melt glass consistent with extreme thermal events, and all of this distributed across 4 continents at the same stratigraphic level, right at the beginning of a period of rapid and catastrophic climate change, right at the level where the Clovis culture disappears from the archaeological record, and right at the level where 37 genera of large animals begin their march toward extinction. The impact hypothesis does not explain all of this with perfect certainty. No hypothesis does, but it explains more of it, more coherently, than any other single explanation currently available. Let us return now to the people, because at some level, all the geology and chemistry and paleontology is in service of a human story. The story of people who were living full lives on this continent 12,800 years ago, who had families and fears and fire and music and all the things that make a life, and who woke up one morning to find that their world was being unmade around them. We do not know what the event looked like from the ground. We cannot know with certainty, but we can make some educated inferences based on physics and on the evidence left behind, and those inferences are not comforting. If the impact hypothesis is correct, the sky would have changed. Something would have appeared, perhaps a fireball or multiple fireballs visible in daylight, moving fast, breaking apart, the light of it overwhelming the sun for a moment. Then the airbursts, one or many, the sound arriving after the light, a concussive wave of pressure moving outward from the explosion points, flattening trees, knocking animals off their feet, creating a sound that would have been unlike any sound heard before or since by any human ear on this continent. Then, the heat. An invisible thermal pulse radiating outward from each airburst point, not quite touching the ground directly, but close enough that anything dry enough to burn would ignite. Grasslands would have caught first. Then the edges of forests. Then the forests themselves. The smoke would have been visible for hundreds of miles, perhaps thousands. It would have risen into the upper atmosphere and begun spreading. Within days, it would have been circling the globe. Within weeks, enough particulate matter would have been suspended in the stratosphere to begin blocking sunlight, reducing the solar energy reaching the surface, cooling temperatures. This is the same mechanism that caused the nuclear winter scenarios that physicists modeled during the Cold War. Not the explosion itself, but the smoke from the fires. The explosion started that drives the climate change. And there is evidence, independent of the impact debate, that this kind of atmospheric disruption happened at the beginning of the Younger Dryas. The climate records from ice cores and ocean sediment cores show a rapid transition to cold conditions that is consistent with a sudden reduction in solar input, not just with a change in ocean circulation patterns, which is the more conventional explanation for the Younger Dryas onset. The conventional explanation, by the way, is called the meltwater pulse hypothesis. It proposes that the Younger Dryas was triggered by a sudden influx of cold fresh water into the North Atlantic Ocean, disrupting the thermohaline circulation, the system of ocean currents that moves warm water northward and keeps northwestern Europe relatively mild. The most commonly cited source for this freshwater pulse is the catastrophic draining of a large proglacial lake, Lake Agassiz, a vast body of water that had accumulated behind the retreating Laurentide ice sheet. When an ice dam holding Lake Agassiz broke, the hypothesis goes, enormous quantities of cold fresh water flooded into the North Atlantic, shutting down the circulation and triggering the cold snap. This is a perfectly reasonable hypothesis. The problem is that the geological evidence for the specific flood event that would have triggered the Younger Dryas at the right time has proven elusive. The channels through which Lake Agassiz would have drained have been the subject of intense research, and while there is evidence of large flood events in the region, pinning a specific event to the precise onset of the Younger Dryas has been difficult. The impact hypothesis offers an alternative explanation for the meltwater pulse. If a large object or swarm of objects struck the Laurentide ice sheet, the energy of the impact would have instantly melted enormous quantities of ice. The resulting flood would have been sudden, massive, and exactly what is needed to disrupt the thermohaline circulation. The impact explains the meltwater pulse. The meltwater pulse explains the cooling. The cooling, combined with the direct effects of the impact itself, explains the rest. It is an elegant chain of causation. Whether it is the correct chain of causation remains to be seen. But let us stay with the human story for a moment longer, because there is something that tends to get lost in the scientific debate, something that deserves to be said clearly. Whatever caused the Younger Dryas, whatever produced the YDB layer, whatever triggered the extinctions and the climate change, and the disappearance of the Clovis culture from the archaeological record, the people who lived through it were real. They were not footnotes. They were not data points in a sediment column. They were people. They were people who watched the animals they had learned to hunt, the animals their parents and grandparents and great-grandparents had learned to hunt, disappear. Not all at once, probably, not in a single catastrophic moment that anyone alive could witness from beginning to end, but over the course of a lifetime, over the course of a generation or two, the mammoths became rare, and then rarer, and then gone. The horses, the animals that North American ecosystems had produced and sent out into the world, that had returned with European settlers thousands of years later to become so iconic that we cannot imagine the American West without them, the horses went first, from abundant to scarce to memory. The Clovis culture, with its distinctive fluted spear points and its apparently continent-spanning networks of stone exchange, essentially disappears from the archaeological record at this horizon. What follows is not a void, not a literal extinction of the human population, but a fragmentation. The archaeological cultures that appear in North America after the Clovis horizon are more localized, more varied, more adapted to specific regional conditions. The broad, connected culture that made Clovis points from Florida to California contracts into smaller, more isolated groups, making their own distinct tools for their own distinct environments. This is consistent with what you would expect from a population that has been severely reduced and disrupted. When a human community loses access to the resources and the networks and the ways of life that sustained it, it does not simply vanish. It adapts. It contracts. It finds new strategies. But it changes, sometimes so completely that the connection to what came before is visible only in the broadest terms, in the bones and in the genetics, not in the technology or the material culture. There is genetic evidence that the population of North America went through a severe bottleneck at approximately this time. A bottleneck is what population geneticists call an event in which the size of a population is drastically reduced, causing a loss of genetic diversity. If you sequence the genomes of ancient remains from before and after the Younger Dryas boundary, you can see signatures in the genetic data that are consistent with a population crash and subsequent recovery. This does not tell you what caused the population crash. It does tell you that something happened that dramatically reduced the number of people on this continent around 12,900 years ago. The people who survived were not the inheritors of a stable, thriving civilization. They were the remnants of one, and they had to rebuild in a changed landscape, with changed animals, under a changed climate, without the accumulated knowledge and networks that the Clovis culture had represented. Think about what it means to lose the megafauna, not in an abstract, ecological sense, but in a practical, survival sense. The mammoths and mastodons were not just food, they were materials. Their hides were shelter, their bones were tools. Their ivory was worked into everything from spear shafts to personal ornaments. A successful mammoth hunt could sustain a group of people through months of scarcity. When the mammoths were gone, not just the calories disappeared. The entire technological and cultural system that had been built around them had to be rebuilt from the ground up. The same was true of the horses. Horses would not return to North America until Spanish conquistadors brought them in the 16th century. And when they did, the effect on the indigenous cultures of the plains was transformative within just a few generations. That transformation gives us a window, inverted, into what the loss of horses must have meant 12,000 years earlier. Everything that horses made possible, the speed of travel, the ability to carry loads, the reach of hunting parties across wide landscapes, all of that disappeared with the extinction. The ground sloths are perhaps the strangest loss to contemplate. Giant ground sloths left behind enormous claw marks in caves and on cliff faces across South America and into the American West. The marks are at a height that suggests animals standing upright, reaching up with massive forelimbs, the way a bear sometimes stands to scratch a tree. They were herbivores, apparently, browsers that fed on leaves and fruit in forests. They were not predators, but they were a presence in the landscape, enormous and slow-moving and strange, and then they were not there anymore. We do not know what the Clovis people thought of the ground sloths. We do not know if they hunted them, avoided them, incorporated them into their stories and their spiritual understanding of the world. We do not know if any of them watched the last sloth die and understood what they were watching. We only know that after a certain point in the sediment record, the sloth bones stop appearing in association with human artifacts, and then they stop appearing altogether. The continent that the post-Clovis peoples inherited was a diminished place, not worthless, not lifeless, not without beauty or resources, but stripped of a significant portion of its largest, most dramatic fauna. The ecological roles that those large animals had played, the grasslands that mammoths had maintained through their grazing and trampling, the seeds that giant sloths had dispersed through their enormous digestive tracts, the scavenging opportunities that their carcasses had provided for dozens of other species, all of those roles were vacated. The ecosystems reorganized themselves in the absence of their largest members, and they are different from what they were, different in ways that may be difficult to fully appreciate, because we have no living memory of what came before. Now let us talk about Kennewick Man, and about Spirit Caveman, and about the broader question of who the first Americans actually were, because it turns out that this question is even more complicated and even more politically fraught than the impact debate. In TZ Deviatset Devidasart Shest, 2 college students wading in the Columbia River near Kennewick, Washington, found a human skull. The skull turned out to belong to a nearly complete skeleton that was subsequently dated to approximately Osum Pietset years ago. The skeleton, which became known as Kennewick Man, immediately became one of the most contested artifacts in the history of American archaeology. The controversy had multiple dimensions. The legal dimension was about who had the right to control the remains. The Native American Graves Protection and Repatriation Act, passed in Tseets Deviatset Devadasat, gave Native American tribes the right to claim ancient remains found in the United States if they could demonstrate a cultural affiliation with those remains. Several tribes, including the Confederated Tribes of the Umatilla Indian Reservation, claimed Kennewick Man and sought to have him reburied without scientific study. A group of scientists sued, arguing that Kennewick Man was so old and so different in his skeletal morphology from modern Native Americans that cultural affiliation could not be established, and that denying scientists access to the remains would constitute an irreplaceable loss of scientific knowledge. The case wound through the courts for years before the scientists were ultimately allowed to study the skeleton. The scientific dimension of the controversy was about what Kennewick Man's bones could tell us about the peopling of the Americas. Some researchers argued that his skull morphology was more similar to Southeast Asian populations, specifically to the Ainu people of Japan, than to most modern Native American populations. This sparked speculation that there might have been an early wave of migration from coastal East Asia, arriving by boat along the Pacific coast, that predated or was separate from the Siberian land bridge migrants, who are generally assumed to be the ancestors of most modern Native American populations. The genetic dimension became clearest in Dvatisitsa Patnast, when a team of researchers published the results of DNA sequencing from Kennewick Man's skeleton. The results were clear and somewhat counterintuitive given the morphological debate. Genetically, Kennewick Man was most closely related to modern Native American populations. He was not a representative of a separate, earlier wave of Asian migration. He was, genetically speaking, family to the people who claimed him. This did not resolve all the questions raised by his bones. The relationship between skeletal morphology and genetics is complex, and it is possible that early American populations showed more physical variation than modern populations do, variation that has since been reduced by subsequent population dynamics. But it did suggest that the simple narrative of 2 or more distinct waves of migration, each with a different ancestral source population, was probably not correct, or at least was not as clean as some had hoped. Spirit Cave Man, found in Nevada and also dating to approximately Deviat 2's Rista years ago, raised similar issues. His skeletal morphology was also described as different from typical modern Native American forms, and his remains were the subject of a lengthy legal dispute between the Nevada State Museum and the Fallon Paiute Shoshone tribe. When DNA was finally extracted and sequenced in Dvatisitsa Shesnarst, the results were similar to Kennewick Man. Spirit Cave Man was genetically most closely related to modern Native Americans. What these ancient genomes are telling us collectively is that the peopling of the Americas was a complicated process that we are still working to understand, but that there is a fundamental genetic continuity between the earliest Americans and the indigenous people of the Americas today. The question of how many waves of migration there were, what routes they took, and what happened to the populations that were here before those waves remains open, but the idea that the first Americans were a completely separate and mysterious people with no connection to modern Native Americans does not hold up to the genetic evidence. This matters for our story because it means that the descendants of the people who survived the Younger Dryas catastrophe, whatever it was, are still here. The genetic line did not break. It was bent severely by whatever happened 12,900 years ago, but it did not break. The people who rebuilt their lives in the diminished, changed continent that followed the Younger Dryas are the ancestors of the people who built the mound complexes of the Mississippi River Valley, who constructed the cities of Cahokia and Chaco Canyon, who developed the sophisticated agricultural systems of the American Southwest and the Amazon Basin, who created the empires of Mesoamerica and South America. All of that came after. All of that grew from the survivors. But let us not rush past the survivors themselves, because their story deserves attention. The 1,000 years of the Younger Dryas were not uniformly catastrophic. The cooling and disruption were most severe in the northern hemisphere, and particularly in regions closest to the ice sheets. In the southern portions of North America, in Central America, in South America, the climate change was real but less extreme. Populations could and did maintain themselves, adapt, find new resources, develop new strategies. The archaeological record from these regions in the Younger Dryas period is sparse, as it always is from periods before agriculture and permanent settlement left substantial physical traces, but it is not empty. There is evidence of continued human presence at sites throughout the Americas during the Younger Dryas. The people did not vanish. They contracted and fragmented and adapted. They moved. Groups that had been spread across wide territories pulled back to areas where resources were more reliable. Groups that had been in contact with each other across hundreds of miles of landscape lost those connections as populations decreased and territories shrank. The broad, interconnected world of the Clovis, people gave way to smaller, more isolated communities developing in parallel, each finding its own solutions to the problems of surviving in a changed world. This process of isolation and independent development is visible in the archaeological record as a proliferation of distinct regional cultures, each with its own tool technologies, each adapted to its own specific environment. The people of the Pacific Northwest developed a culture built around salmon and cedar and the resources of the coast. The people of the Great Basin developed a culture built around the seasonal movements of game and the harvesting of pine nuts and other plant foods in a semi-arid landscape. The people of the eastern woodlands developed a culture built around the rich forests and river systems of that region, hunting deer and elk and turkey, gathering nuts and berries, beginning the slow process of plant manipulation that would eventually lead, thousands of years later, to agriculture. None of these cultures called themselves descendants of the Clovis people. They almost certainly had no memory, no oral tradition that reached back to the specific moment of the Younger Dryas catastrophe. 12,000 years is a very long time for an oral tradition to survive unchanged. But they were, in a biological and a cultural sense, the continuation of the story that the Clovis people had been living when the world changed. There is something profound about that continuity, something that tends to get lost in the scientific debate about impact markers and sediment layers and megafaunal extinctions. The people survived, against whatever odds the Younger Dryas presented, across whatever catastrophe the YDB layer represents. The human line continued, changed, diminished, fragmented, but unbroken. And in the thousands of years that followed the Younger Dryas, the human population of the Americas rebuilt itself with extraordinary creativity and resilience. The agricultural revolution came to the Americas independently of its origins in the Middle East, arising from the cultivation of maize and beans and squash in what is now Mexico, of potatoes and quinoa in the Andes, of sunflowers and goosefoot. In eastern North America, the population grew. Settlements became permanent. Permanent settlements became villages. Villages became towns. Towns became cities. Cahokia, a city built on the banks of the Mississippi River in what is now the state of Illinois, was, at its peak around Tissetsto CE, one of the largest cities in the world. Its central mound, Monk's Mound, contains more earth than the Great Pyramid of Giza. At its height, Cahokia may have been home to as many as 20,000 people, making it larger than London at the same period in history. And yet most Americans have never heard of it. Chaco Canyon in New Mexico was the center of a sophisticated culture that built massive stone great houses. The largest pre-Columbian structures north of Mexico laid out roads across hundreds of miles of desert, maintained an astronomical system precise enough to align their buildings with solar and lunar events, and operated a trade network that brought turquoise from distant mines, Masors from Mexico, copper from the Great Lakes. Chaco was abandoned around Tissit-Sto-Paidsart CE, for reasons that are still debated, drought being the most popular explanation, but it represents a level of organizational complexity and long-distance coordination that challenges any simple narrative of pre-Columbian North America as a land of isolated, simple communities. These achievements did not emerge from nothing. They grew from the long, slow accumulation of knowledge and adaptation that began with the survivors of the Younger Dryas catastrophe. They were built on a foundation of ecological knowledge, of plant and animal management, of astronomical observation, of social organization that had been developing for thousands of years. The Clovis people who vanished from the record 12,800 years ago were not the dead end of a story. They were the beginning of a longer story, one whose chapters we are still, in many cases, only beginning to read. Let us talk about what we do not know, because in a mystery this old and this complex, the things we do not know are at least as important as the things we do. We do not know, with certainty, whether the Younger Dryas was caused by an extraterrestrial impact. The evidence is suggestive. In the view of many scientists who have spent years studying it, it is compelling. But it is not yet conclusive in the way that the Chicxulub impact is conclusive, where we have a crater, a worldwide iridium anomaly, and a clear and unambiguous mass extinction event all lined up in perfect correspondence. The Younger Dryas impact hypothesis is still a hypothesis. We do not know with certainty what caused the megafaunal extinctions. The most honest answer is probably that it was a combination of factors, human hunting pressure and climate change, working together in ways that neither, alone, would have been sufficient to cause. The Younger Dryas impact, if it occurred, would have been a third factor, a sudden catastrophic disruption that pushed already stressed populations over the edge. But the relative contribution of each factor to the final extinction of each species is unknowable with our current evidence. We do not know what the Clovis people called themselves, or what they believed, or what stories they told around their fires at night. We know their technology. We know from the distribution of their distinctive spear points that they were connected across enormous distances, that stone was traded or people traveled hundreds of miles across the continent. We know, from the bones they left behind and the animals they hunted, and the way they processed their kills, something about their diet and their ecological knowledge. But we know almost nothing about their inner lives, their cosmology, their understanding of themselves, and their place in the world. We do not know whether there is a continuous oral tradition, preserved in any of the indigenous cultures of the Americas today, that reaches back to the Younger Dryas, and preserves some memory of whatever happened at the beginning of that period. There are traditions among many Native American peoples that speak of great floods, of catastrophic fires, of a time when the world was different and many animals that no longer exist were still alive. Whether any of these traditions preserves a genuine memory of events 12,000 years ago, transmitted faithfully across 500 generations, is impossible to say with certainty. The human capacity for oral tradition is remarkable, but 12,000 years is at the very outer edge of what any oral tradition has been demonstrated to preserve. We do not know whether the impact hypothesis, if confirmed, would constitute a genuine paradigm shift in our understanding of human prehistory, or whether it would simply add a detail to a story whose broad outlines are already known. My own intuition is that it would be transformative. The idea that a catastrophic extraterrestrial event shaped the trajectory of human civilization in the Americas, that the cultures we know, from the great mound builders to the Aztecs and Inca empires, were all built in the long shadow of a cosmic catastrophe, that their most distant ancestors survived, changes the way we understand those cultures and their achievements, not diminishes them, deepens them. There is a theory, proposed by some researchers working in the field of archaeoastronomy and ancient mythology, that ancient peoples around the world preserved memories of cosmic catastrophes in their mythological traditions, encoding the memory of comets and impacts and floods in stories that were told for thousands of years before writing allowed them to be recorded. The work of researchers like Emilio Spedicato, Victor Clubb, and Bill Napier, And more recently, Graham Hancock, who is controversial but whose work has helped bring the impact hypothesis to a wider audience, suggests that the ancient sky was a more dangerous and dramatic place than we tend to assume, and that the mythological traditions of ancient peoples may contain more accurate astronomical memory than we have been inclined to credit. This is speculative territory. It goes beyond what the geological and archaeological evidence can directly support, but it raises a question worth sitting with. What would it mean to the descendants of the Clovis survivors, to the people who built Cahokia and Chaco Canyon and the great cities of Mesoamerica, if they had preserved, in their stories and their rituals and their astronomical observations, some echo of the catastrophe that their ancestors survived? What would it mean to know that the sky is not always safe, that the universe does not always leave humanity alone, that the world can change violently and suddenly in ways that no amount of preparation or knowledge or skill can prevent? It would mean, I think, that the impulse to watch the sky carefully, to track the movements of celestial bodies with precision, to align the great structures of your civilization with the movements of the sun and moon and stars, was not merely aesthetic or religious in a purely symbolic sense. It was practical. It was the practice of a people who knew, at some level, even if they could not articulate it in the terms we would use today, that the sky had once done something terrible, and might do it again. The great observatories of the ancient world, from Stonehenge in England to the medicine wheels of the American Great Plains to the astronomical alignments of Chaco Canyon, are usually explained in terms of agriculture, of knowing when to plant and when to harvest, and they did serve that function. But they may also have served another function, the function of watching, of not being caught unaware again. This is speculation, I want to be clear. It is not something that can be confirmed by a sediment sample or a genome sequence, but it is the kind of speculation that emerges naturally from sitting with the evidence, from trying to imagine what it was like to be a human being in a world where the sky had once fallen. Let us turn now to the question that haunts the edges of this entire discussion, the question that is rarely asked explicitly in the scientific papers, but that is always present in the background. Could it happen again? The answer is yes. Not the Younger Dryas specifically, not the same event repeated, but the general category of event, a large extraterrestrial object striking the Earth with enough energy to cause significant disruption to the climate and the ecosystems, is not merely a historical possibility. It is a physical certainty at some point in the future. The question is not whether it will happen, but when and how large, and whether we will see it coming in time to do anything about it. The scientific community has recognized this risk and has developed programs to survey the sky for near-Earth objects, asteroids and comets, whose orbits bring them close to the Earth and whose trajectories might, at some future point, intersect with our own. The SpaceGuard survey and its successors have catalogued thousands of near-Earth objects and have dramatically increased our awareness of the population of potentially hazardous bodies sharing the solar system with us. We have also, for the first time in history, demonstrated the ability to actually deflect an asteroid when the DART mission in 2022 successfully changed the orbit of a small asteroid called Dimorphos by slamming a spacecraft into it at high velocity. So we are not entirely helpless. We have the knowledge and, in principle, the technology to protect ourselves from at least the class of threats that we can see coming with enough warning. What we cannot protect ourselves from, at least not yet, is the kind of fragmented comet or debris swarm that the Younger Dryas impact hypothesis describes, a cloud of objects spread across a wide area of space, some of them too small to track individually, arriving over a wide area and delivering their energy in multiple airburst events rather than a single large impact. The Taurid meteor stream, an annual meteor shower visible from Earth every October and November, is believed by some researchers to be the remnant of a large comet that fragmented thousands of years ago. Among the researchers who take the Younger Dryas impact seriously, some have proposed that the object or objects responsible for the event were part of the Taurid stream or were associated with a parent comet whose descendants still cross the Earth's orbit today. If this is correct, the Earth passes through the densest part of the Taurid stream twice a year, and embedded within that stream may be objects large enough to cause significant damage if they were to enter the atmosphere. This is a sobering thought. It is also, from a scientific standpoint, something that can be investigated. The Taurid stream is real. Its potential for containing large embedded objects is real. Whether any of those objects pose a near-term threat is a question that better sky surveys and more detailed orbital calculations could, in principle, answer. But let us come back to the past, because the present and the future, however important, are not what this particular story is about. The story is about the people who were here before, the people who built a civilization, in the broad sense of that word, a way of life adapted to the specific richness of a specific continent that was disrupted or destroyed by something we are still struggling to understand. The people whose descendants rebuilt and rebuilt again, and whose achievements in the thousands of years between the Younger Dryas and the arrival of European ships in the 15th century were extraordinary by any measure. And the story is about the mystery itself, about what it means to look at the geological record and see, preserved in a thin, dark layer of sediment, the signature of something that changed the world, and to not yet be able to say with complete confidence what that something was. The uncertainty is uncomfortable, as uncertainty always is, but it is also, in a way, a gift. It is an invitation to keep looking, to keep asking, to resist the comfort of simple explanations in favor of the harder work of actually understanding what happened. The Clovis people did not leave us written records. They could not warn us about what was coming. They could not document what they experienced when the world changed around them. But they left us their tools, their bones, their hearths, and their campsites and their kill sites. They left us the genetic legacy that persists in the bodies of their descendants. They left us, in the sediment layers where their culture disappears, a mystery that is worth the work of solving. Because, at some level, their mystery is our mystery. The question of what happened to the first civilization of the Americas is not just a historical curiosity. It is a question about vulnerability, about what happens when a complex, adapted, successful way of life encounters a disruption it was not prepared for, about how communities survive catastrophe, and what they build from the ruins. The Clovis people, or the people who came before them, and whose story we are only beginning to reconstruct, faced something. We do not know exactly what. We know it was large. We know it was fast. We know it changed their world in ways that took thousands of years to recover from. And we know that despite all of this, their story did not end. It continued. It grew. It produced everything that came after. That is not a small thing. There is a lake in South America called Lake Quitzo in the Mexican state of Michoacán, and at the bottom of that lake, in sediment cores drilled from the lake bed, researchers found the YDB layer. They found it with its suite of markers, the platinum anomaly, the nanodiamonds, the carbon spherules, the magnetic spherules, all of it right where it should be if the impact hypothesis is correct. This site is far to the south of the North American sites, where the evidence was first identified. It is in a different country, a different ecosystem, a different cultural tradition, and it shows the same markers at the same level. The same is true of sites in Belgium, of sites in Syria, at a place called Abu Huraira, where the first farmers in the world were beginning to practice agriculture when the Younger Dryas struck and disrupted everything. Of sites in South Africa, the YDB layer is not a regional phenomenon. It is not an artifact of North American geology or North American archaeological biases. It appears wherever people have looked for it carefully enough, at the same moment in time, across 4 continents. And at each of those sites, the same question hangs in the air. What caused this? What was it that left this signature simultaneously across 40% of the Earth's surface? What kind of event produces nanodiamonds and platinum anomalies and melt glass and carbon spherules from Chile to Belgium to South Africa at the same stratigraphic level? The honest answer, the answer that the evidence currently points toward most strongly, while acknowledging that the debate is not over, is that something came from space. not necessarily a single large impactor. Perhaps a swarm of smaller objects, a fragmented comet, or a particularly dense cluster of debris, delivering its energy across a wide area through multiple airbursts rather than a single catastrophic impact. The total energy delivered could have been equivalent to many nuclear weapons, not concentrated at a single point but spread across a continent, each individual airburst local in its immediate effects, but collectively contributing to a global atmospheric disruption. This kind of event is not unprecedented in the historical record. The Tunguska event of 10 Deviates, the Chelyabinsk meteor of 2013, which exploded above a Russian city with an energy equivalent to roughly 30 times the atomic bomb dropped on Hiroshima, injured over 1,000 people and damaged thousands of buildings, and was small by comparison to what the YDB evidence implies. Scale up the Chelyabinsk event by a factor of 10,000 or 100,000 and distribute it across a continent, and you begin to approach what the YDB layer may be recording. We should talk about the scientists who have spent their careers on this problem, because they deserve to be named. Richard Firestone of the Lawrence Berkeley National Laboratory was one of the primary authors of the original 2007 paper that formally proposed the Younger Dryas impact hypothesis. James Kennett of the University of California, Santa Barbara, a geologist of impeccable reputation with a long career studying climate change and ocean sediments, became one of the most committed advocates for the hypothesis after examining the evidence. Alan West, a geophysicist, has been central to the effort to identify and characterize the YDB markers at sites around the world. Christopher Moore of the University of South Carolina has contributed some of the most compelling evidence from sites in the American Southeast. Ted Bunch, a geologist and meteor expert, has contributed expertise on the impact-related minerals found in the YDB layer. These are not fringe scientists. They are researchers with long careers and genuine expertise in the fields relevant to the hypothesis. They have published in peer-reviewed journals. They have responded to criticism with more data rather than with rhetoric. They have, over the nearly 2 decades since the hypothesis was first proposed, added sites, refined methods, addressed objections, and continued to find evidence that they believe supports the hypothesis. The critics are also scientists of genuine expertise and good faith. They have raised real methodological concerns. They have pointed to genuine ambiguities in the data. They have performed independent analyses that sometimes did and sometimes did not replicate the original findings. The debate has not been a simple case of good scientists versus bad scientists or mainstream versus fringe. It has been a genuine scientific argument about genuinely difficult evidence conducted in the places where scientific arguments are supposed to be conducted, in the journals and at the conferences and in the laboratories. And, as of the time of this telling, the argument has not been resolved, but the weight of evidence has, over time, shifted somewhat. More sites, more independent confirmations, more markers that are difficult to explain by conventional means. The hypothesis has not been falsified. It has, in the view of many researchers who follow this field, become progressively harder to dismiss. What would it take to settle the debate? Probably 2 things. First, a comprehensive, independent, well-funded effort to examine the YDB layer at many sites simultaneously, using standardized methods, with multiple laboratories analyzing splits of the same samples so that methodological differences between labs can be identified and controlled for. This would cost money and effort, but it is not technically beyond what current science can do. Second, a better understanding of the specific mechanism of exactly what kind of object or objects could have produced the observed distribution of evidence. Computer modeling of the impact scenarios has been done, but it has been done with limited resources and with significant uncertainties in the key parameters. Neither of these things has happened yet, largely because the hypothesis remains controversial enough that major funding agencies have been reluctant to commit significant resources to investigating it. This is one of the stranger aspects of the sociology of this debate. The hypothesis is significant enough to be widely discussed and argued about, but not yet accepted enough to attract the kind of systematic, well-funded investigation that would either confirm it or definitively refute it. It exists in a kind of scientific limbo, too credible to ignore, too uncertain to act on definitively. There are people working to change this. Researchers who believe the evidence is strong enough to warrant serious investigation are pressing for more resources and more systematic study. Institutions like the Comet Research Group, an informal collaboration of scientists from multiple fields who are committed to investigating the impact hypothesis, continue to publish new findings and to advocate for more attention to the question. The question, to be clear, is not merely academic. If a large extraterrestrial event did trigger the Younger Dryas, then we live in a solar system where such events have occurred within the human era, within the span of anatomically modern human civilization. That changes the risk calculus. It changes the urgency of understanding the distribution of potentially hazardous objects in the solar system. It changes what we need to know about our own history and about our own vulnerability. And it changes, in a subtler way, our understanding of ourselves. The great civilizations of the ancient Americas, and indeed of the ancient world generally, built their knowledge systems and their institutions and their belief systems in the aftermath of a catastrophe that we have, until recently, not understood was a catastrophe. They built their world in the shadow of something terrible that they may or may not have remembered clearly. The impulse to watch the sky, to record the cycles of the heavens with precision, to build structures that aligned with solar and astronomical events, may have been partly born of a deep, transmitted awareness that the sky is not always benign. There is something moving about that, something that makes the achievements of those ancient peoples feel both more impressive and more poignant. They rebuilt, against the odds, in a diminished world, with reduced populations and disrupted ecosystems and lost technologies. They rebuilt. They developed agriculture, constructed cities, maintained astronomical observations for thousands of years, created art and music and story and all the things that make a civilization worth calling a civilization. And they did all of this while carrying, somewhere in their cultural memory, the shadow of a time when everything had been different, a time before the world changed. We are the heirs of all of it, of the Clovis culture and of the Younger Dryas survivors and of the long, slow rebuilding and of the great civilizations that came after. The genetic line runs unbroken from the people who were standing on this continent 12,900 years ago to the people who are alive today. Changed, mixed, complicated by all the migrations and conflicts and cultural exchanges of the intervening millennia, but unbroken. There is a site in Florida called the Page-Ladson site, a sinkhole in the Orcilla River where, under the water and the sediment, archaeologists have found evidence of human occupation dating back approximately 14,500 years. They have found a mastodon tusk that bears what appear to be cut marks made by stone tools, evidence that humans were processing mastodon carcasses in Florida more than 14,000 years ago. They have found stone tools. They have found the bones of animals that no longer exist. And they have found all of this underwater because the site is now submerged beneath a river that was dry land 14,000 years ago. This is what the rising sea levels at the end of the Ice Age did to the archaeological record of the earliest Americans. The coastal peoples, the ones who may have followed the coastline south from the Bering Land Bridge, the ones who built their camps and their communities on the rich shores of the late Pleistocene world, left most of their traces in places that are now underwater. Their sites are not lost, they are submerged. And as underwater archaeology and the technology for locating and excavating submerged sites has improved, we are beginning to find them, beginning to recover fragments of those earliest chapters of the American story from beneath the waves where the rising sea buried them. Page-Ladson is one such site. There will be others. The continental shelves of North and South America were exposed land during the last glacial maximum, land that human beings lived on and left traces on. As we develop the tools to find and excavate those traces, the story of the first Americans will fill in, becoming richer and more detailed and more surprising than we currently imagine it. And somewhere in that fuller story, the Younger Dryas event will occupy its proper place, Not as an obscure geological datum, not as a footnote in the debate about megafaunal extinctions, but as a turning point. A moment when the world that the first Americans had built over thousands of years was disrupted, possibly catastrophically, and when the long work of rebuilding began. The work that eventually produced everything we know. The mound builders, and the canyon dwellers, and the plain runners, and the forest keepers, and the coastal fishermen, and the desert farmers, and the mountain herders, and all the thousands of distinct cultures that Europeans encountered when their ships arrived on these shores in the 15th century. All of that grew from what survived the Younger Dryas. All of that is the legacy of the survivors. We are still learning their story. We are still finding their traces, still arguing about what the evidence means, still developing the tools we need to read the record that the ancient world has left us. The debate over the Younger Dryas impact hypothesis will eventually be resolved one way or another. New sites will be found, new analyses performed, new questions asked of old samples. The sediment holds its secrets patiently. It has been holding them for 12,900 years. It can wait a little longer for us to develop the wisdom and the methods to read them correctly. But the people who stood on this continent before the world changed, the people who survived the change and rebuilt from the ruins, the people whose descendants carried the genetic and cultural inheritance of all those thousands of years forward into the world that Europeans found when they arrived. Those people do not have to wait. Their story is here. It is in the soil, in the bones, in the genes, in the sediment layer that bears the marks of something extraordinary. And it is worth knowing, not just for the scientific puzzle of it, not just for the historical curiosity of it, but because it is part of the human story. The part of the human story that happened here on this continent before anyone was writing things down. The part that was nearly lost and was not lost. The part that survived. The Clovis people, whatever else they were survivors of a harsh and beautiful world. And when that world changed around them, some of them survived that too. They left descendants. Those descendants left descendants. The line continued, through the Younger Dryas, and through the long rebuilding, and through all the centuries of growth and change and conflict and creativity that followed, all the way to the present moment. To the people who live on this continent today, to the people who carry, in their DNA, the traces of those ancient populations, to the people who, if they stand very still and listen very carefully, might hear in the oldest stories of this land some echo, however faint and transformed by time, of the world that existed before the sky changed and the animals went away and everything had to be built again from the beginning. That echo is real. It is in the stones and the soil. It is in the bones of the animals that are no longer with us. It is in the thin, dark layer of sediment that holds, in microscopic particles of diamond and glass and spherical metal, the chemical signature of something that came from beyond our world and touched this one in a way that was never forgotten, even when the memory of it became so old that it turned into myth, and then the myth turned into the landscape itself, and the landscape held the secret in its layers, the way the land always does, patiently, without judgment, waiting for someone to come along and ask the right questions. We are asking them now. The answers are coming slowly, the way answers to real questions always do, but they are coming. Let us go deeper into the archaeology, because the physical objects that people leave behind tell stories that words never could, and the story that the Clovis-era sites tell is one that has been getting richer and more complicated with every decade of excavation. The Clovis spear point is a remarkable object. It is not a stone that was sharpened into a rough point by bashing it against another rock. It is a precisely engineered tool made by someone who understood the fracture mechanics of flint, obsidian, chert, or whatever local stone was available, with an intimacy that can only come from years of practice. The distinctive feature of a Clovis point is the flute, a long, narrow flake removed from the base of the point on one or both sides, creating a groove that allowed the point to be mounted more securely and more aerodynamically onto a shaft. This fluting technique is difficult. Modern knappers who have spent years learning to work stone in the traditional way still find it one of the most challenging steps in point production, because a single mistake at that stage, A miscalculation of angle or force will shatter a point that took hours to shape. The fact that Clovis points are found across the entire continent, from the Pacific coast to the Atlantic, all made with the same distinctive fluting technique, tells us something important about the people who made them. They were connected, they shared knowledge, or they shared ancestry, or both. The technique spread across an enormous geographic range in a remarkably short period of time, suggesting either a rapid spread of a single founding population or an unusually effective network of cultural transmission. The raw materials of Clovis points tell a similar story. Many Clovis points were made from stone that came from sources far from where the points were found. Points discovered in Virginia and the Carolinas were sometimes made from stone that had been quarried in Pennsylvania or Ohio. Points found in the Southwest were made from obsidian traced to volcanic sources hundreds of miles away. This was not accidental proximity. Stone was being moved deliberately across large distances, which means people were either traveling those distances themselves or were passing materials through exchange networks that spanned the continent. Clovis kill sites, places where the bones of large animals were found in close association with Clovis tools, give us glimpses of the hunting strategies these people employed. At the Lena Ranch site in Arizona, 11 mammoths were found along with the bones of horses, tapirs, and bison, all associated with Clovis tools. At the Murray Springs site, also in Arizona, a kill site preserved the bones of a mammoth and several bison along with the tools used to process the carcasses. At the Dent site in Colorado, the bones of at least 12 mammoths were found with Clovis points. The pattern that emerges is of hunters who targeted large animals, who may have driven them into water or bog or rough terrain where their mobility was limited, who worked in groups to bring down animals that no individual could have handled alone, and who processed the carcasses efficiently, taking the most nutritious parts and leaving behind the parts that were less useful. But Clovis sites are not only kill sites. There are campsites, places where people stopped for extended periods, made tools, prepared food, and left behind the kind of domestic debris that accumulates wherever people live. The Galt site in Texas is one of the most significant of these. It has been excavated over many years and has yielded not just Clovis materials but pre-Clovis materials as well, an older layer beneath the Clovis layer that has been dated to before 13,000 years ago, and that includes stone tools that are different from Clovis in their technology and form. The Galt site is one of the strongest pieces of evidence that Clovis was not the first culture in North America, that there were people here before the Clovis tradition developed, people using different tools and presumably living in different ways. What we are beginning to see, as the excavation and analysis accumulates, is a picture of pre-Columbian North America that is far more complex and dynamic than the simple narrative of Clovis first and then everything else suggests. There were multiple populations, possibly with different origins, possibly arriving by different routes at different times, interacting and exchanging, and sometimes competing across a continent that was rich enough to support all of them. The Clovis culture, when it appeared, did not appear in a vacuum. It emerged from an existing human presence on the continent, and it spread across that presence with a speed and uniformity that still demands explanation. The explanation that some researchers have proposed is that the Clovis tradition spread not because a single founding population expanded to fill the continent, but because a particularly effective technology, the fluted point and the hunting strategies that went with it, was adopted by populations that were already spread across the continent, in the same way that a useful innovation spreads through connected human communities in any era. The fluted point was a better tool for hunting certain large animals than what had come before it, and so it spread, carried by traders and travelers, and adopted by people who encountered it and recognized its advantages. If this is correct, then the Clovis horizon in the archaeological record represents not the arrival of a new people, but the spread of a new technology through a population that was already there. And the disappearance of Clovis from the record after the Younger Dryas represents not the extinction of a people, but the abandonment of a technology that no longer served its primary purpose, the hunting of large animals, because the large animals were gone. This is a subtler story than the narrative of arrival and extinction. It is harder to tell and harder to understand, but it may be closer to what actually happened. Let us think about the landscape itself. The land that the Clovis people and their predecessors lived on was not the land we know today. The continent was younger, in the sense that the features we take for granted, the specific courses of rivers, the distribution of forests and grasslands, the locations of lakes, were all different. The Great Lakes did not exist in their current form. The Mississippi River system was different. Enormous pro-glacial lakes that no longer exist spread across the northern portions of the continent, fed by the meltwater of the retreating glaciers. The coastline was different, extended further out into what is now the ocean because sea levels were lower. The vegetation was different. The grasslands of the Great Plains supported different communities of grasses and forbs than they do today. The forests of the East were different in their species composition, some species more abundant, some less, some absent altogether. The climate was different, not just in temperature, but in seasonality, in rainfall patterns, in the timing of the seasons. The animals that lived in this different landscape were adapted to it in ways that had developed over millions of years. The whole system was in dynamic equilibrium, the kind of balance that is always provisional and always subject to disruption, but that had nevertheless been maintained across thousands of previous generations. When the Younger Dryas struck, it disrupted that equilibrium. The cooling was rapid by geological standards. Ecosystems that had been slowly adjusting to the warming of the post-glacial period suddenly had to contend with a reversal, a return toward cold conditions that was fast enough to outpace the ability of many species to adapt. The vegetation shifted. The grasslands contracted in some areas and expanded in others. The forests changed. The rivers and lakes behaved differently. The timing of the seasons on which so much of ecological life depends was disrupted. For the large animals, this was particularly challenging. Large animals have slow reproductive rates. A mammoth does not replace itself quickly. A mastodon pregnancy lasts approximately 22 months. If the survival rate of calves drops, if the birth rate falls, if the death rate rises even slightly, the population can decline faster than it can replace itself. And once it declines past a certain point, recovery becomes mathematically unlikely. The crash can come suddenly, even if the causes have been building slowly. And if you add to that the pressure of human hunting, even hunting that had been sustainable for thousands of years, the combination can be lethal. A population that is already stressed by climate disruption is far more vulnerable to hunting pressure than a healthy, growing population. The hunters do not even have to change their behavior. The same number of hunters taking the same number of animals per year can push a declining population over the edge when it would not have done so to a stable or growing population. This is the most honest version of the story we can tell with current evidence. Multiple causes, interacting in ways that amplified each other. The Younger Dryas climate disruption, possibly triggered by an extraterrestrial event, stressed the megafaunal populations. Human hunting, which had been sustainable under normal conditions, became unsustainable when the populations were already stressed. The two pressures together produced an extinction that neither alone might have caused. Whether you add a third cause, the direct effects of an extraterrestrial impact, the fires, the thermal pulse, the atmospheric disruption, depends on how convincing you find the YDB evidence. The impact proponents argue that the direct effects of the event itself, independent of the climate change it may have triggered, were sufficient to push many species over the edge in the immediate aftermath. The critics argue that the YDB evidence does not support an event of sufficient magnitude to have that kind of direct effect. The answer to this question, too, is still being worked out. Now let us take a step back and think about what this story means for our understanding of American history more broadly. Because there is a way in which the events of 12,900 years ago cast a long shadow over everything that came after, including the period that is usually where American history begins, Sousa, the arrival of Europeans in the 15th and 16th centuries. The European encounter with the Americas was, among many other things, an encounter with a continent whose human history stretched back at least 15,000 years. and whose ecological history had been shaped by human presence for all of that time. The forests that Europeans saw when they first arrived on the eastern coast of North America were not pristine wilderness. They were the product of thousands of years of indigenous management, of selective burning, of tree cultivation, of the ecological effects of hunting and gathering practices that had shaped the landscape as surely as any deliberate agricultural intervention. What looked to European eyes like a vast, untouched wilderness was actually a humanized landscape, managed in ways that European concepts of agriculture and land use were not equipped to recognize. The ecological context of that humanized landscape had itself been shaped by the extinctions of 12,000 years earlier. The forests of the eastern seaboard were different from what they would have been had the megafauna survived. The grasslands of the interior were different. The distribution of plant and animal species was different. The continent that Europeans encountered in the 15th century was the continent that had spent 12 millennia recovering from the Younger Dryas catastrophe and rebuilding its ecosystems in the absence of many of the large animals that had previously played major ecological roles. This matters because it complicates any simple narrative of pre-Columbian America as a pristine, Edenic wilderness that was then degraded by European settlement and exploitation. The continent had already been through one catastrophic disruption, had already lost a large fraction of its megafauna, had already undergone the ecological reorganization that followed those extinctions. The indigenous peoples who lived on the continent when Europeans arrived had adapted to and were managing a landscape that was itself the product of a previous ecological catastrophe. Their ecological knowledge, their land management practices, their understanding of the plants and animals and soils and waters of the continent were all calibrated to that post-catastrophe landscape. And when European diseases swept through the indigenous populations of the Americas in the 16th and 17th centuries, killing in some estimates 90% of the population within a century of first contact, the ecological effects were dramatic and long-lasting. The depopulation of the Americas removed the human management from landscapes that had been managed for thousands of years, allowing forests to regrow where there had been cultivated fields and managed woodlands, changing the fire regimes that indigenous burning had maintained, altering the population dynamics of animals that had been hunted and managed by human communities for generations. Some researchers have argued that what Europeans interpreted as pristine, untouched American wilderness in the 17th and 18th centuries was actually the ecological aftermath of the demographic catastrophe of the 16th century, a rewilded landscape that had been recovering for a century or more from the sudden removal of human management. The wilderness was not original, it was a wound. All of this connects, if you follow the thread carefully, back to 12,900 years ago. The first catastrophe, the Younger Dryas, produced the first major disruption of the human ecological system of the Americas. The recovery from that disruption, over 12,000 years, produced the rich and complex indigenous civilizations that Europeans encountered. The second catastrophe, the demographic collapse of the 16th century, produced the second major disruption. The ecological recovery from that second catastrophe, which is still ongoing, is what we call the American wilderness. Understanding the first catastrophe is essential to understanding everything that followed it. It is the foundation of the story, the event that shaped the conditions in which everything else happened. Let us talk now about the sites themselves, about the specific places where the evidence of the Younger Dryas boundary has been found, and about what those places tell us about the event and its effects. The Sheridan Cave site in Ohio is a small sinkhole that preserves an extraordinary record of the Younger Dryas transition. At this site, researchers found the bones of dozens of species of animals, including many that went extinct at or around the YDB, all concentrated in a tight stratigraphic sequence that records the passage from the pre-Younger Dryas world to the Younger Dryas world in remarkable detail. Within the YDB layer at Sheridan Cave, researchers found elevated concentrations of magnetic spherules and other impact markers, adding this site to the growing database of YDB localities. What makes Sheridan Cave particularly valuable is the density of the faunal record. The bones include not just megafauna but small mammals, birds, reptiles, amphibians, and fish, all of which help to reconstruct the environment at the time of the transition. The picture that emerges is of a rapid and dramatic shift in the animal community, with some species disappearing abruptly at the YDB level and others appearing or becoming more common afterward, consistent with a significant disruption of the ecosystem at that moment. The Blackwater Draw site in New Mexico, the site where the first Clovis points were found in the Tsedes Deviatset Dvarsits, has been excavated many times over the decades, and its stratigraphy is among the most studied of any North American archaeological site. The YDB at Blackwater Draw corresponds to a layer of carbonaceous material that has been interpreted as evidence of burning, and the Clovis cultural materials disappear abruptly below this layer, consistent with the broader pattern of Clovis disappearance at the YDB horizon. The Murray Springs site in Arizona, one of the most significant Clovis kill sites ever excavated, also shows a distinctive layer at the boundary that separates the Clovis materials below from a different cultural tradition above. At Murray Springs, this layer is sometimes called the black mat, a thin, dark band of organic material that has been found at multiple southwestern sites at the same stratigraphic level. The black mat has been interpreted in various ways. Some researchers see it as evidence of increased moisture at the YDB, consistent with the climate disruption of the Younger Dryas. Others see it as evidence of the burning event associated with the proposed impact. Whatever its origin, the black mat is real, and it is consistent across sites. It marks a boundary in the archaeological and ecological record that is as clear as anything in the late Pleistocene stratigraphy of North America. Above the black mat, no Clovis tools. Below the black mat, no evidence of the cultural traditions that followed Clovis. The mat is the boundary, and the boundary corresponds to the Younger Dryas onset. There is a site in Arizona called the Eloise site that has produced some of the most intriguing evidence yet for the direct effects of the proposed impact event. At this site, researchers found a layer containing not just the standard suite of YDB markers, but also melted and fused sediment grains that appear to have been subjected to extremely high temperatures, higher than any ordinary wildfire could produce. The morphology of these grains, the way they have been melted and then rapidly solidified into glassy spheroids, is consistent with what you would expect from material that was exposed to the thermal pulse of a nearby airburst. At the Younger Dryas boundary layer in Belgium, at a site called Oman, researchers found elevated concentrations of platinum along with magnetic spherules and other markers. Belgium is far from North America, across an ocean, on a different continent. The fact that the same suite of markers appears at the same stratigraphic level in Belgium as in Arizona and South Carolina adds significantly to the global character of the event. A regional wildfire or a local geochemical anomaly cannot explain evidence found simultaneously on opposite sides of an ocean. The Abu Huraira site in Syria is particularly poignant when you consider it in the context of the Younger Dryas event. Abu Huraira was occupied by some of the earliest farmers in the world, people who were in the process of transitioning from a hunter-gatherer way of life to a more settled, agricultural existence at precisely the moment when the Younger Dryas struck. The disruption of the Younger Dryas would have been particularly devastating for these early farmers who were beginning to depend on the reliable seasonal growth of cultivated grains. When the climate shifted rapidly toward cold and dry conditions, the crops would have failed, the stored reserves would have been exhausted, and the communities that had been tentatively experimenting with agriculture would have been forced to abandon that experiment and return to more mobile, opportunistic foraging strategies. And yet agriculture eventually triumphed. The Younger Dryas ended, the climate warmed again, and the populations that had survived the cold millennium returned to the Fertile Crescent and began again the slow, halting process of plant domestication that would eventually produce the agricultural revolution. The fact that they did so, that human communities in the Middle East recovered from the Younger Dryas disruption and went on to develop agriculture and then civilization, is another example of the extraordinary resilience that characterizes our species. The same resilience was displayed by the peoples of the Americas, though their path was different. In the Americas, agriculture developed independently from different plant species in different regions over a longer timescale. The disruption of the Younger Dryas may have set that process back by thousands of years. It may have eliminated nascent experiments in plant cultivation that were underway among some Clovis or pre-Clovis communities, but it did not eliminate the human capacity for innovation, and eventually the process resumed. Let us consider what the Americas might have looked like, ecologically and culturally, had the Younger Dryas not occurred. This is a speculative exercise, counterfactual history, but it is a useful one for thinking about the magnitude of what was lost. Without the megafaunal extinctions, the ecological structure of North America would have been profoundly different. The presence of mammoths and mastodons, of horses and camels, of giant ground sloths and large predators like the short-faced bear and the American lion would have maintained different patterns of vegetation, different distributions of seeds and nutrients across the landscape, different dynamics in the grasslands and forests. The landscapes that early agricultural communities would have encountered, if agriculture had developed in North America as it developed in the Middle East and East Asia, would have been different in fundamental ways. The horses, in particular, are an interesting case to contemplate. Horses are extraordinary animals from a human technological perspective. They can carry loads, pull vehicles, travel long distances, and change the speed and range of human movement in ways that fundamentally alter what is possible for human societies. The civilizations of the Old World that had access to horses and later to cattle and other large domesticated animals were able to develop in ways that the civilizations of the Americas, which had none of these large domesticated animals, with the partial exception of llamas and alpacas in the Andes, could not. The absence of large domesticable animals in the Americas after the Younger Dryas extinctions is one of the key factors that Jared Diamond identified in his famous analysis of why Eurasian civilizations came to dominate the world in the factig last few centuries. If the horses had survived, if the camels had survived, if the megafauna that were lost at the Younger Dryas had persisted, the civilizations of the Americas might have developed along very different lines, might have achieved very different capabilities, might have been in a very different position to respond to the arrival of European ships in the 15th century. This is one of the most profound consequences of the Younger Dryas event, if the extinctions were indeed primarily driven by that event rather than by human hunting. The extinctions did not just remove a set of animals from the landscape, they removed a set of potential domesticates. They narrowed the range of large animals available for human use to a small fraction of what had existed before. And that narrowing had consequences that rippled forward 12,000 years, shaping the trajectory of human civilization in the Western Hemisphere in ways we are only beginning to appreciate. Now let us sit with the mystery for a moment, because the mystery deserves to be held in its full complexity rather than being rushed past in the eagerness to explain it. 12,900 years ago, something happened. We know this because the sediment says so. We know it because the animals say so, or rather, because their absence says so. We know it because the archaeology says so, in the disappearance of the Clovis tradition from the record. We know it because the genetics says so, in the signatures of a population bottleneck. We know it because the ice cores say so, in the chemical markers of atmospheric disruption. We know it because the climate record says so, in the evidence of rapid, dramatic cooling. What we do not know is exactly what the something was. We have a candidate, a large extraterrestrial impact or airburst, and we have evidence for that candidate that is growing in breadth and in some respects in strength. But we do not have the kind of definitive, undeniable confirmation that would settle the debate once and for all. We have a mystery that is becoming less mysterious with time, but that has not yet fully yielded its secret. And there is something appropriate about that. The mystery is old. It has kept itself for 12,000 years. It will give up its last secrets at its own pace, on its own schedule, in response to the patient work of the scientists who who are still digging and analyzing and arguing and publishing and refining their understanding. Science is not fast, and mysteries this old are not quickly resolved. But they are resolved, eventually. The truth, whatever it turns out to be, is in the sediment. It is waiting. In the meantime, we have the story of a continent that was home to an extraordinary variety of large animals and to the people who lived among them. The story of an event that disrupted that world so thoroughly that very little was left unchanged. The story of the survival, of the long, slow, creative, resilient rebuilding that followed. The story of the civilizations that eventually grew from that rebuilding, the mound builders and the canyon dwellers and the great empires of Mesoamerica and South America. The story of all that was lost and all that was saved and all that grew from the saving. It is a very long story. It began before writing and before cities and before most of what we normally think of as history. It begins in the oldest chapters of the human presence in this hemisphere, in the traces left by the first people who walked these landscapes and hunted these animals and sat by these fires and looked up at these stars. The stars, incidentally, are still there. The same stars that the Clovis people navigated by, the same constellations that, whatever shamans or storytellers or astronomers existed among the first Americans read and interpreted and built their understanding of the cosmos around, are still visible in the night sky. Slightly shifted in their positions due to the precession of the equinoxes, the slow wobble of the Earth's axis that changes which stars are near the celestial pole over thousands of years, but still the same stars, still the same patterns of light in the same vast dark. And somewhere in the North American night sky, visible as a faint smear of light on clear nights far from city lights, is the Milky Way, the galaxy we live in, the river of stars that every human culture, since the beginning of symbolic thought, has noticed and named and built stories around. The Clovis people saw it, the people who survived the Younger Dryas saw it. Every generation since, the Mississippian mound builders and the Pueblo people and the Plains nations and all the others whose cultures stretched across the millennia between the Younger Dryas and the European arrival, all of them saw it, and we see it still when we take the trouble to look. There is something in the fact of that continuity, in the fact that the same sky has been watching human life on this continent for at least 15,000 years, that puts the mystery of the Younger Dryas in perspective. The event was catastrophic by any human measure. It disrupted a civilization, caused the extinction of dozens of species, triggered 1,000 years of climatic hardship, and left marks in the geological record that we are still arguing about. But the human story continued. The sky watched, and the story continued. That is the most important thing to understand about the Younger Dryas, about the Clovis people, about the mystery of what happened to America's first civilization. Whatever it was that happened, it was not the end. It was a rupture, a terrible disruption, a loss that we cannot fully measure because we do not know what might have been built had the disruption not occurred. But it was not the end. The end has not come yet. The story is still being told. You are part of it, in ways that stretch back further than any written history can reach, back to the people who survived the Younger Dryas and built a new world from the fragments of the old one. Their resilience is part of your inheritance. Their curiosity is part of what moves through you when you want to understand things, when you want to know what happened and why and what it means. The mystery of the Younger Dryas is a mystery about all of us, about what we have come from and what has been lost along the way, and what has survived and what that survival means. It is a mystery worth sitting with, worth turning over in the mind, worth carrying into the quiet hours of the night, when the analytical mind relaxes its grip and the older, deeper parts of the mind, the parts that connect us to all the generations who have sat by fires and looked at stars and wondered about the world, begin to speak. Those older parts of the mind know something that the analytical mind tends to forget. They know that questions are as valuable as answers, that the willingness to sit with a mystery, to resist the comfort of premature resolution, to keep looking even when the looking is hard, is itself a form of intelligence. The most ancient form, probably. the one that kept our ancestors alive through ice ages and catastrophes and the collapse of worlds. They kept looking. We are still looking. And what we find, when we find it, will be worth the wait. There is one more thread worth pulling before we let this story settle into sleep, and it concerns the ways that oral traditions and ancient mythology may preserve, however transformed by time, some memory of events that happened before any writing existed to record them. The idea that oral traditions can preserve accurate information across very long periods of time has been gaining traction in recent years. We have already mentioned the Australian Aboriginal traditions that preserve memories of coastlines that were flooded by rising sea levels more than 7,000 years ago. The research behind this finding, published by researchers Patrick Nunn and Nicholas Reed, examined dozens of stories from Indigenous Australian communities and found that many of them described specific geological features that had been present before the end of the last ice age but had been submerged by rising sea levels. The stories had been transmitted with sufficient accuracy over hundreds of generations to preserve a recognizable description of the pre-flood landscape. This is remarkable. It suggests that human oral traditions can, under the right conditions, function as a kind of geological memory, preserving accurate information about the physical world across timescales that seem impossibly long to anyone raised in a culture that relies on written records. The conditions that enable this kind of long-duration memory are not fully understood, but they seem to involve the embedding of practical geographical or ecological information in stories that are given sacred or ceremonial significance, ensuring that they are transmitted carefully and accurately, rather than being freely embellished in the way that purely entertainment-oriented narratives might be. With this in mind, consider some of the mythological traditions of the indigenous peoples of North America. Many of these traditions include accounts of catastrophic events, of fires and floods, and the disappearance of animals that were once abundant. The Lakota tradition speaks of a great flood that came after a period of moral disorder. Many California Indian traditions include accounts of a great fire that swept the land. The Cherokee have traditions about a time when the world was covered in ice. The Ojibwe have stories about the great beings that once lived alongside humans and are now gone. None of these traditions, taken individually, constitutes evidence for the Younger Dryas impact hypothesis. Myths about floods and fires and vanished animals are found in cultures all around the world, and they can be generated by many different experiences and many different cultural needs. A story about a great fire does not necessarily preserve a memory of a specific historical fire. A story about vanished animals does not necessarily preserve a memory of a specific extinction event. But the pattern is interesting. The convergence of themes across traditions that developed independently, in geographically distant communities, is at least consistent with the possibility that some of these traditions preserve transformed memories of real events. Not memories that can be read as literal accounts of what happened, but memories that encode, in the symbolic language of myth, something of the emotional and experiential reality of a world that was disrupted. The researchers who study this question most carefully tend to be cautious about claiming more than the evidence supports. The connection between specific mythological traditions and specific geological or astronomical events is almost always ambiguous. There are too many degrees of freedom in the interpretation, too many ways that a story could have originated that do not involve the preservation of ancient memory, for any single identification of a myth with a specific event to be made with confidence. But the broader point, that oral traditions can preserve accurate information across very long periods of time when the conditions are right, is now supported by enough independent evidence to take seriously. And the question of whether any of the indigenous traditions of North America preserve some echo of the Younger Dryas, however faint and transformed, is a legitimate research question. It is one that requires collaboration between archaeologists, geneticists, climate scientists, and specialists in indigenous oral traditions, and it is a collaboration that is beginning to happen in some research communities. The people who might know most about this question, of course, are the indigenous peoples themselves. The holders of the oral traditions, the knowledge keepers, the elders whose role in their communities has been to preserve and transmit the stories across generations. Their perspectives on the question of what their traditions might preserve and how they should be interpreted by outsiders are essential to any serious engagement with this topic. And historically, the relationship between academic researchers and indigenous communities on questions of this kind has been troubled by a long legacy of appropriation and misrepresentation that makes trust difficult to build. This is changing slowly. There are researchers who are working to build genuine collaborative relationships with indigenous communities who are approaching these questions with respect for indigenous knowledge systems rather than the assumption that Western scientific frameworks are the only valid way of understanding the world. The results of these collaborations, where they have occurred, have often been illuminating in ways that neither partner could have achieved alone. The story of the Younger Dryas and its effects on the human populations of the Americas is, among other things, a story about the ancestors of people who are still alive today. The indigenous peoples of the Americas are not relics of a past that is over. They are the present, the living continuation of a human story that has been unfolding on this continent for at least 15,000 years. Their knowledge of their own history and their own traditions is part of the evidence we need to understand what happened in the deep past, and it deserves to be treated as such. There is a broader point here about the way we understand history. The conventional Western model of history begins with writing. Before writing, there is prehistory, a vast shadowy period that we can only approach through archaeology and genetics and climate science, inferring what we can from the physical traces that time has left behind. This model has served well in many ways. It has produced an extraordinary body of knowledge about the human past, but it has also produced blind spots, gaps where the absence of written records has been taken to mean the absence of significant history, where the people who came before writing are implicitly treated as less important, less complex, less worth understanding than the people who came after. The Clovis people and their predecessors and successors had no writing. They left no textual record. But they had history, in every meaningful sense of the word. They had cultures, technologies, belief systems, social organizations, ecological knowledge, astronomical understanding, and the full range of human experience. They had politics and love affairs, and disputes and innovations and tragedies. They had everything that makes a people, and they had it on a continent that they had been inhabiting and shaping and learning from for at least 15,000 years before the first European ship appeared on the horizon. Understanding them, as fully as we can with the limited evidence we have, is not just an academic exercise. It is an act of recognition. A recognition that the human story is longer and more complex and more diverse than the written record alone can capture. A recognition that the people who came before writing were fully human in every sense that matters, and that their history is part of our history, part of the story of what it means to be a human being on this planet. The Younger Dryas is a turning point in that story, a moment when something, whether an extraterrestrial impact or a complex of interacting causes, or some combination we have not yet fully characterized, disrupted a world that had been built over thousands of years and set in motion the long process of rebuilding that eventually produced everything we know about the pre-Columbian Americas. Understanding that turning point, understanding what was lost and what survived and why, is part of understanding ourselves, because we are, in a very real sense, the descendants of survivors. Every human alive today is descended from people who made it through the bottlenecks, the catastrophes, the periods of extreme hardship that punctuate the long history of our species. The Younger Dryas was one of those bottlenecks. The people of North America who survived it were part of the larger story of human resilience that connects the earliest members of our species to every person alive today. That resilience is not something we can take for granted. It is not a guarantee. It has been earned and re-earned, generation by generation, through the application of intelligence and cooperation and adaptability to the problems that each era presents. The Clovis people and their successors earned it. The indigenous cultures that flourished for 12,000 years after the Younger Dryas earned it. The civilizations of Cahokia and Chaco Canyon and the great centers of Mesoamerica and South America earned it. We are the beneficiaries of all that earning, and the mystery of what happened 12,900 years ago is, in a sense, a gift. It is a reminder that the world can change, suddenly and dramatically, in ways that no existing civilization is fully prepared for. It is a reminder that resilience is not automatic, that it has to be built and maintained, that the knowledge and the social structures and the ecological practices that allow human communities to survive disruption are precious and can be lost. The people who survived the Younger Dryas built something from their survival. Over 12,000 years, they built many somethings. Cities, knowledge systems, agricultural traditions, astronomical observatories, trade networks, artistic traditions of extraordinary beauty and sophistication. All of it built in the long aftermath of catastrophe. All of it evidence of what human beings can do when they survive something terrible and choose to build rather than merely endure. We are still in that building. The story has not ended. The mystery has not been fully solved. The debate about what caused the Younger Dryas and what its effects were is still ongoing, still generating new research and new arguments and new evidence. The understanding of who the first Americans were and how they came to this continent is still being refined and revised with every new excavation and every new genome sequence. And in the background of all of this, the sediment holds its record. The thin, dark layer at the Younger Dryas boundary, with its nanodiamonds and its platinum anomaly and its magnetic spherules and its melt glass, waits patiently for the science to catch up with it. It has waited for 12,900 years. It can wait a little longer. The truth is in there. We will find it in the fullness of time, in the careful, patient, argumentative way that truth is always found. And in the meantime, the mystery remains. Beautiful and serious and deeply human in the way that all great mysteries are human, because they remind us that we are small and the world is large and the universe is larger still, and that something happened here once, something vast and strange and terrible, and that we are still here, still asking, still looking up at the same sky that those first Americans looked up at, wondering what it might do next. Think about what it means to be a mystery that is 12,000 years old. To have sat in the sediment through the rise and fall of dozens of civilizations, through the development and collapse of empires that never knew you existed, through the entire recorded history of humanity on this planet. The Younger Dryas boundary layer was there, underground, holding its evidence. While the Egyptians built their pyramids, and the Greeks wrote their philosophy, and the Romans built their roads, and the medieval cathedrals rose in Europe, and the printing press was invented, and the ships crossed the Atlantic, and the Industrial Revolution transformed the world, and 2 world wars shook everything again, and the digital age arrived and changed everything once more. Through all of that, the sediment held its secret. The platinum was there, the nanodiamonds were there, the melt glass and the magnetic spherules and the carbon spherules were all there waiting. They were there the whole time we were looking for other things, looking at written history, at named rulers and recorded battles and documented inventions, at the parts of the past that left themselves in forms we knew how to read. While we were doing that, the sediment was keeping its own record, patient and indifferent and complete in its own way. The scientists who finally started asking the right questions of that record, who developed the analytical techniques to read what the sediment had been trying to say, are doing something profound. They are expanding the readable past. They are adding chapters to the human story that were always there, but that no one had previously known how to open. That work is not finished. It has barely begun, if we are honest about the scale of what remains to be understood. The Americas alone cover more than 42 million square kilometers. The relevant sediment layers are spread across that entire area, buried under thousands of years of subsequent deposition, hidden in lake beds and river channels and cave floors and coastal shelf sediments that are now underwater. The number of sites that have been examined for YDB markers is in the dozens. The number that could be examined with sufficient resources and sufficient time is in the millions. We have sampled a tiny fraction of the available evidence. What the full evidence will eventually tell us When and if we find the resources and the will to collect it remains to be seen. But the direction the evidence has been pointing, consistently and increasingly clearly, is towards something extraordinary. Something that challenges the comfortable assumption that the long sweep of human prehistory in the Americas was a simple story of migration and adaptation and gradual development, with no major external disruptions. Something that requires us to take seriously the possibility that the sky has touched this continent in living human memory, geological memory, if not historical memory, in a way that changed everything. That possibility is worth sitting with. It is worth the discomfort of uncertainty. It is worth the intellectual honesty of saying we do not know for certain, while also saying the evidence is pointing in a direction that deserves our serious attention. Science at its best is exactly this: the willingness to follow the evidence wherever it leads, even when it leads to uncomfortable or counterintuitive places, while maintaining the rigor to distinguish between evidence and wish, between pattern and noise, between what we know and what we hope. The Clovis people, 12,900 years ago, did not have the luxury of that kind of careful, patient inquiry. Whatever they faced it in real time, without warning, without the analytical tools to understand what was happening or why. They faced it with nothing but the knowledge they had accumulated, the relationships they had built, the resilience that their ancestors had encoded into their biology and their culture over hundreds of thousands of years of human survival. And some of them made it through. We owe them that acknowledgement, not in a sentimental way, not as a form of nostalgia for a world that is gone, but as a straightforward recognition of what their survival made possible. Everything that came after, every civilization and culture and tradition and innovation that the Americas produced in the 12,000 years between the Younger Dryas and the present moment, was built on the foundation of their survival. They are not distant ancestors in some abstract genealogical sense. They are the direct progenitors, biological and cultural, of everything that followed them on this continent. Their mystery is our inheritance. Their resilience is part of what we are made of. And their story, however incomplete our knowledge of it remains, is worth knowing as fully as we can manage. Worth the excavation and the analysis and the argument and the revision that are the tools of the scientific enterprise. Worth the collaboration and the respect and the humility that genuine engagement with indigenous knowledge requires. Worth the patience to sit with uncertainty rather than rushing to premature resolution. Worth, perhaps, a sleepless night spent listening in the dark, turning it over in the mind, letting the strangeness and the weight of it sink in. There is a particular kind of awe that comes from standing at the edge of what is known and looking into what is not. Scientists who work on the deep past describe it regularly, that feeling of being in the presence of something enormous that has not yet fully yielded itself to understanding. The Younger Dryas boundary sits at exactly that edge. We can see it in the sediment. We can measure it. We can argue about what it means. But the full shape of what happened, the lived experience of the people who were there, the sound and the light and the terror of whatever descended on that world 12,900 years ago, all of that is beyond our reach. We can approach it. We can infer it. We can reconstruct fragments of it from the chemical and biological and genetic traces it left behind. But we cannot enter it. We cannot know it from the inside, the way the people who lived through it knew it. That gap between what the evidence shows and what the experience was is where the mystery lives, and it is a gap that no amount of scientific progress will ever fully close. Some things about the past are gone completely, not just undiscovered but irrecoverable. And sitting with that irreversibility, with the honest acknowledgement that some questions will never be answered, no matter how carefully we look, is itself a kind of wisdom. 12,900 years ago, something happened, something enormous. The sediment knows, the bones know, the genes know, and slowly, one careful paper at a time, one carefully excavated site at a time, one refined analytical technique at a time, we are learning to read what they have been trying to tell us all along. The first civilization of the Americas did not vanish without a trace. It left its traces everywhere, in the soil and the stone and the sky and the people who are still here, still living on this land, still carrying in their biology and their traditions and their stories some faint, transformed, persistent echo of a world that existed before the catastrophe and survived it and was rebuilt and kept going. That is what human beings do. They keep going, even when the world changes, even when the sky falls, even when everything that was known and relied upon is suddenly and violently transformed. They keep going, and eventually they make something new from what remains. We are part of that something new. All of us, everywhere on this planet, are the descendants of people who kept going through things that should have stopped them. That is the deepest truth the Younger Dryas has to teach us. Not just about the first Americans, about all of us, about what we are capable of when the world demands it. I appreciate you listening. If you enjoyed the story, drop your thoughts in the comments. I'd love to read them.